Hey guys, RLA Jack here with a rundown of pretty much everything covered in Lab 0.2. And I wanted to do this video particularly either as a way to enhance your experience with this lab by giving you a little bit more information on what everything is about, and also as a way to help you troubleshoot or review your answers for this lab. So hopefully you'll get something great out of this. I'm not going to give you the answers to it, but I am going to teach you what the things in that lab are all about, like possibly on a deeper level than you need to know at this point. So first off, there's something called the transpose. So we have our matrix A, and we can do A transpose. And what it does is it turns each row into A, this 1, 2, 3, into a column, each row into a column, and also each column is a row. Effectively, a matrix has something called a main diagonal. That's its 1, 1, 2, 2, and so on. It just flips the matrix across its main diagonal to get the transpose matrix. For almost everything you'll ever do in MATLAB, this just normal transpose will work just fine, but there is this other thing called the, well, it's technically not just transposing, it also does something called the Hermitian transpose. So this will actually become apparent if I work with complex numbers. So, of course, vectors. A row vector would just do exactly what you think. It would turn into a column, but I'm going to put some complex numbers in this. So I'm going to do 1 plus 3i, 2 plus 4i, maybe 6, and then maybe 8 minus 8i. I don't know, I typed that sort of stupid, but here we go, complex numbers. And whenever I do B transpose, oh no, look, the signs flipped on all the pluses. All the pluses became minuses, this 0 just stayed 0, and this minus became a plus. So this is effectively switching the sign of the complex part of each entry in the vector. So to fix that, you can use dot before the transpose, and that is fixed. So anytime you're working with complex numbers or you're writing math software for complex numbers, even if you aren't using complex numbers at the time, you should really be cautious of transpose versus dot transpose. But for the most part, at this point in the course, you just need to know that transpose turns rows into columns and columns into rows. Alright, so the next thing I'm going to show you is multiplication of matrices. So let me make a companion for A, maybe 2, 3, 4, 5. And I do A times, oh, I forgot to assign it to something. Let's call this capital C. If I do A times C, C times A, that would work. You'll notice that I just did matrix multiplication. I display C and A. So I took this first row, multiplied it by this first column, 2 times 1 plus 3 times 4 makes 14, so on and so forth for all 6 in the final product. So this is matrix multiplication. If you don't know about it, I will show you a video on it. I have a playlist called Matrices for CAAM 210 on my channel that you should probably look at, and that's going to tell you just about everything you need to know in this course about matrices and basic linear algebra. But I did not make the videos myself. I used Khan Academy. So if I try A times C though, you'll notice that matrix dimensions have to agree. So in order to do a row times a column, you have to have the same number of columns in the first matrix as rows in the second. So if I do A times C, and I just look at size A and size C, you'll notice that I have 2 rows in A and 3 columns, and I have 2 rows in C and 2 columns. So I need the same number of columns in A as I do rows in C, and it turns out I have 3 columns in A, 2 rows in C, so I cannot multiply A by C. But if I do C by A, I have 2 columns in C and 2 rows in A, so that works just fine. And that's pretty much it for matrix multiplication. There's nothing too much to worry about. Okay, so now the idea of concatenation. So, oh yeah, also vectors are just matrices, in case you didn't know. So I'm gonna make a vector D equal to 1 semicolon 2 semicolon 3. It's a column vector, and if I do A times D, surely enough it'll multiply it. And if I look at size of A and size of D, you can see the 3's match up. So yeah, matrix vector multiplication is just matrix multiplication because vectors are just matrices. But that's that. So concatenation. So I have A and C, which are 2 by 3 and 2 by 2, right? And I can stick them together. So if I want to glue C to the right side of A, I can just do open bracket A comma C, and just like 2 elements, if you're making a row vector, you know, like open bracket 5 comma 7, like in this thing, sticking 5 and 7 next to each other, doing A comma C will stick A and C next to each other. Likewise, A transpose is like that. So if I do 5 semicolon 7, it'll do that and create a column vector. It'll stack them on top of each other. But if I do A transpose, which is 3 by 2, semicolon C, it will just stack the 2 matrices on top of each other. Now keep in mind, the dimension has to match for concatenation to work. Otherwise, you're not going to have a good time. So if I just wanted to do A semicolon C, A which has 3 columns and C which has 2, it will not work. So actually there's a command called vertcat that's actually being run when you do the semicolon thing, and if I try and do A transpose comma C, which don't have the same number of rows, horscat. So if you ever see a vertcat or horscat error, it is definitely something with a concatenation that you're doing, but it sort of tells you that in there. So that works. Okay, basic operations on matrices. So you of course can add and subtract matrices, as I already showed you in that video. So if I take maybe F is equal to 1, 2, 3, 4, and G is equal to 5, 6, 7, 8. Then if I do F plus G, it will give me the sum of F and G. If I do F minus G, it'll do it. Also element-wise sum, or difference. If I do F times G, though, MATLAB doesn't know that I'm not doing matrix multiplication. So I have to actually do something a little bit different. I'm going to have to do something called dot times or dot divide. So if I have 2 matrices, F and G, which are the same size, I can do F dot times G, and that will multiply the element in F by the corresponding element in G to get the corresponding element in F times G. Likewise, F dot divide G will do the exact same thing element-wise, but with division. And it's really easy to miss this. Actually, if you just do F divide G, it will actually give you an answer for some stupid reason. And it has to do with weird, like, upper level linear algebra and like least squared error and stuff. But other than that, you shouldn't freak out too much. Okay, so you also can square matrices. So if I want to do something like f squared, square each element in f, which is a row vector, I can't. So I need to actually compute element-wise power, which is dot exponent, or dot caret. So if I do f dot squared, surely enough, it'll square each element in f and put it in the answer, in the corresponding position. I can also do 2 dot to the f, and it will compute the exponent of each position to the power at the particular position in f. So you can do this. Also, you can put whatever numbers you like into any of these. So that also helps. And then as far as basic operations, oh yes, so sometimes one error that people make is c, which is this, and I want to square c. It's real tempting just to do c squared, and it will give you the answer, but this is the result coming from matrix multiplication of c and c. If you want the actual square of each element, you have to do c dot squared, and that will do the job for you. Also, pretty much everything I'm saying also applies to matrices in full, as long as they're the same dimensions. Okay, so the next thing I want to tell you about is the colon expression. So the colon expression is a simple way to create spans of numbers. So if I do like 1 colon 5, then it counts from 1 to 5 going by 1. If I do 10 colon 18, it'll go from 10 to 18 going up by 1. And actually, if you go 2.5 to 7.5, it'll go from 2.5 to 7.5 counting up by 1, even though these are decimals. So that's what just a normal colon does. All of these have had a difference between the first and last number that's an integer, but you can actually do it that's not an integer. So if I do 1 to 4.9, it'll actually not ever give me a number that's larger than the number that ends my colon expression. So if I do 1 colon 4.9, it'll give me 1, 2, 3, 4, but it will not give me 5 because 5 is larger than 4.9. Okay, so that's the simple colon expression. So you often use these whenever you want to put indices into a matrix, but I'll explain what that is later. Like pick multiple rows, but you can also do a number in the middle to tell me how much to count up by. So say I want to do 1 colon 5 again, but instead of doing just 1 to 5, I want to count up by 1/2. So if I do 1 colon 1/2 colon 5, I have effectively done it. I get 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5. So that's how you would use a non-1 thing in the middle of the colon expression. Say I wanted to count up by 3s. Well, I only get 1 and 4 because if I went up by another 3, I would get 7, and that's greater than 5. Also, you can count down. So say I was not happy with 1 colon 5, and I instead wanted 5 colon 1, which gives MATLAB a weird result that basically says, okay, I'm trying to count up from 5, I get 6, that's more than 1, so I already stop, and I end up with nothing in my matrix. So I can actually do 5 colon minus 1 if I want to count down by 1, or count up by minus 1, colon 1, and that surely enough will give me 5 through 1 counting down. Okay, so that's basic colon expressions. This isn't exactly in Lab 0.2, but I want to tell you about linspace also at this time. So if I do linspace of 5, 1, and I want to have 5 numbers in it, it will basically have the first element be 5, the last element be 1, and I would have 5 numbers in the overall series, each one the same distance from the last. So that's another way you can build stuff. So it's really useful whenever you don't want to divide stuff out. Say I want to do from 10 to pi squared minus 6, and I want to count up by, I don't know, have 10 increments. I don't even know what pi squared minus 6 is, or if it's greater than 10, but I do know, since this is lin spaced, that my result will have exactly 10 elements, and they will be linearly spaced. So this is my result, and this is actually pi squared minus 6. Okay, so now I'm going to show you how to solve basic systems. But first, I think doing indexing with vectors is probably the first thing. So if I have h, and I'm going to make it equal to a 1 colon 0.5 colon 7, and I want the fifth element in h, I can do h of 5, and that will pull in my fifth element in h. And it works for any one-dimensional vector. So if this is a column vector instead, then h of 5 is also still 3. But you can see that this might get a little complicated when it comes to matrices, because you need 2 numbers to say exactly where you are. So going back to a, if you do a of 1, yeah, it gives you 1, but it starts to count funny. And like if I do a of 4, it'll go 1, 2, 3, 4, and give you this 5. So you need 2 indices when dealing with matrices. And you can basically give the row number first, so 2, and the column number 3. So if I do a of 2, 3, that'll give me 6. Also, if you ever want the last column or the last row, say I wanted the last element on the first row, I can do a of 1 comma end, and end is just a substitute for the highest valued index in that dimension for that object. So a of 1 comma end, it'll say, okay, what's the size of a in the second dimension? It's 3, so that end becomes 3. Surely enough, this is equivalent to a of 1 comma 3. Okay. You can also stick multiple things. So say you want to do a of 1 and 2 comma end. This will give you the first row and the second row on the end. Say you want to do a of 1 and 2 for the first and second rows and first and third columns. This will give you the first and second row and first and third column and their intersection. Say you want to do all columns, but just want the first and say you just want the first row, and you want all columns. You can do a colon, and colon just says in matrix indexing, do all columns. Oops, I just accidentally ran a colon, because if you highlight something and press enter, it runs just what you highlight. So this will give me the first row and all columns. And then finally, suppose that out of A, I wanted just the last row, and I wanted all columns of that. Then I just do a of end, comma, colon, no numbers, and this will give me the last row and all columns, regardless of whether or not I actually know the size of this matrix. Okay, so now I can show you maybe F and G again. If I do G of F of 1, or F of 3, what this does, or it evaluates as the third element in F, and then that returns as 3, so it's now asking G of 3, which is exactly equivalent now, which is the third element in G, which is 7. So that's something you can do. And this actually allows you to use matrices as a mapping from some particular list of numbers, and that's like the dimension or the number of elements in that vector, to a different set of numbers. And I actually use this to make some crazy efficient code for one of our old labs a few years back. It changed it from being like running in 10 hours to about 3 minutes just because of that one fix. Okay, so matrix indexing and systems. Okay, so systems is what I'm going to cover next. So you know the whole AX plus B, or sorry, AX equals B. So if I did something like maybe make my matrix called J, and I'll make it 2, 3, 6, 7, and I'll make K a column vector, 2, 1 maybe, and then I wanted to know what's the solution to Jx plus K, where X is a column vector. Again, you might look at the matrices for CAAM 210 playlist I have. Then you can just do J backslash, it's right below your backspace key and above your enter key, K. Once you do that, it'll give you your solution. You can also use this backslash for linear regression because it essentially has least squares already fit into it through some nice properties of the singular value decomposition. But that's a topic for another time. However, regression is exceptionally easy using MATLAB. Also, keep in mind if your matrix is not n by n and a n by 1 vector, you will not have, you'll either be like under constrained or over constrained, and if the dimensions still match somehow, you will end up getting a regression type result. Okay, so now I'm going to show you a few ways to build matrices automatically. So if I do the command ones of 2, 3, it'll build me a 2 by 3 matrix of ones. Also, I can bracket it in like this with brackets. So I'm giving it a row vector of 2 dimension sizes, and it'll give me that. I can also give it this row vector, and it can give me a 2 by 3 by 4 3-dimensional array, which is sort of printed a little weird since I don't have a 3-dimensional screen. Finally, I can show you what happens if you just pass in a single number, ones of 3, and it'll give you a n by n matrix of ones, or in this case 3 by 3. The same rules apply for zeros. I mean, you can just replace ones with zeros in the command, and indeed you'll replace ones with zeros in your output for all the above inputs. I is a little different. If you just put in a single number, like I have 4, it will give you a 4 by 4 matrix with zeros everywhere except ones along the diagonal. One remarkable thing about this matrix is that it allows you to multiply any dimension matching thing or dimension matching matrix or vector by this matrix, and you will get the same thing. It's called EYE, for in most linear algebra it's just called capital I, and it is called capital I because it is the identity matrix, as in it is the identity element of matrix multiplication. So if I do I of 4 times maybe a column vector 2 semicolon 3 semicolon 4 semicolon 5, it'll give me exactly what I gave it to multiply. Now if I do that times I of 4, though, it will end up giving me an error because dimensions have to agree. I could also take any 4 by 4 matrix. I can multiply by I of 4 on any side, and it would do what I want. Okay, Rand is, again, exact same syntax as zeros and ones, except you can get random numbers out of it. So instead of getting a matrix of zeros or ones, you get a matrix populated with random numbers. So if I had to just do rand of 5, it'll give me a 5 by 5 matrix of random numbers. If I rand of 2, 4, it'll give me a 2 by 4 matrix of random numbers, and so on. Rand I works a little differently because you also have to give it an integer with which to go up to. So it has a maximum integer, and then it has a size. So it might go up to 6, and I might want it to be a 1 by 100 vector of maybe dice rolls, 1 through 6. And surely enough, it'll give me a huge row vector of randomly generated numbers between 1 and 6. Alright, so that's it for a lot of the big matrix generation. Finally, there needs to be this concept of summing matrices. So if I go back to my matrix C, and I want to compute a sum of C, what does sum of C do? Well, it just takes each column and it sums it. It sums along columns because columns are the first dimension, and first is default. So if I do sum of C comma 2, it will instead sum along rows, which are the second dimension. And so there it goes. And if I do sum of C comma 1, you'll just get the same thing as sum of C. This is sometimes useful. I mean, it's rare. One final thing you can do is you can do just as many sums as that matrix has dimensions, and in this case it's a 2D matrix, and it will sum up all elements in the matrix or multi-dimensional array. So say you have just a column vector or a row vector like f. If you just do sum of f, it will not sum the columns of f because each column is trivial and already summed, and so it just sums the rows. Yeah, that's essentially it for everything in this little part. I do think there's one more thing I want to cover before I leave it be on matrices, and that is doing some basic operations to full matrices. So if I do matrix C, and I can do C plus a number, like C plus 1, it will add 1 to all elements. It can also be done 1 plus C. This may not be intuitive, as you might think, oh yeah, dimensions don't match, but MATLAB handles this like a pro. If I do C times 2, even though 2 is technically a 1 by 1 matrix, it's just scalar multiplication. You can also do division. If I wanted to divide 2 by C, I have to use dot divide. Or sorry, 2 dot divide C. I can't do 2 divided by C, because otherwise it starts treating that 2 as a matrix. Okay, so that's it for matrices. I'm going to start my next series on program flow in the next episode. Okay guys, bye.